All right, so this is a problem where I came up with a solution, realized there was a mistake in my solution, thought the entire solution was wrong, but then I realized I was wrong about the entire solution being wrong. So I was right. So let's go ahead with this. So given any n, we're going to define the set. So this hint says to look at the set of points where f is greater than 1 over n. So we're going to call it Cn. This is a set of points where f is greater than 1 over n. All right. Now what I claim is I'm actually going to do this a little differently. I'm going to claim that the measure of Cn is equal to 0. Now what the problem says to do is to prove that this set has content 0. But I wasn't able to come up with a way of doing that, and I also didn't find that to be necessary for this problem. So I wonder if that's a typo, or I wonder if there's a different way that they expected us to do this. But in general, just thinking back to the way that problems like this are done in a measure theoretic setting, I think typically sets like this for general like measurable functions have measurable functions whose integral is 0. I think these sets, you can prove that they have measure 0. I'm not sure if you can prove that they have content 0. In fact, having content 0 is not really a concept that's discussed much in measure theory. So I don't know if this is even true, the fact that this set is content 0. It says in a textbook, so I'm going to guess that they're correct, but I don't really see a way to go about proving that. And furthermore, I don't think it's necessary for this problem, so I'm not going to do it that way. What I will do is what I've stated here. So I'm going to claim that the measure of Cn equals 0. So I wasn't able to come up with a way around arguing by contradiction. So we're going to assume for contradiction that this set does not have measure 0. What does this mean? This means that there is an epsilon such that no cover of Cn has total volume which is less than epsilon. Because for it to have measure 0, that means that given any epsilon, you can find a cover of total volume less than epsilon. But this is not the case because we're assuming that the measure is not 0. Okay, so let P be a partition of A, and U is going to be a subpartition which covers Cn. So if you look at all the elements of U, well, let's do it this way. A subpartition containing all U and P such that, so I'm using U, let's call this V, no, let's call it W. All sets W and P such that W intersected with Cn is non-zero. So if you look at all these sets in this partition, P, any set in there, it's either going to intersect Cn or it won't. If it intersects Cn at all, we're going to put it in this set U. So it's going to be a subpartition containing all sets W which intersect Cn. So that means that any set which is not in U does not intersect Cn. All right. So obviously this collection U covers Cn. All right. So now let's look at this. Let's look at the upper sum of f given P. So this is going to be, let's see here. So it's the sum overall W in U. Now we take the the maximum or the supremum times the volume. And so then we have to add all the things that are not in U. So everything that's in P but not in U. And we do the same thing. All right, now what does this look like? Now we're going to find a lower bound for this. So the second sum, well, let's see here. The second sum we don't really care about. Well, wait, it has to be 0, right? Oh, no, it doesn't have to be 0. Because any element W in P, but not in U, it could have points where F is between 0 and 1 over n. But it doesn't really matter. That's not information we're using for this upper bound. All that we need is... all the information we need is coming from this first sum here. So the second sum, we can just throw it out. Because the sum is certainly going to be greater than or equal to 0 since F is non-negative. So this MWF will be non-negative and the volume will be non-negative, so the whole sum is non-negative. So that's going to be greater than or equal to 0. So that's that. The only thing that we're using is this first sum here. So what we have is it's going to be greater than or equal to W in U. Well, each set W in U intersects Cn, and Cn contains points such that F at that point is greater than 1 over n. So any such set W contains some point where F takes on a value greater than 1 over n. So the supremum of F over all points in W has to be at least 1 over n. So we have 1 over n multiplied by the volume of W. And so the 1 over n, we can pull that out front. And what is the sum of the volumes of all the elements in U? Well, we know that there is an epsilon greater than 0 such that no cover of Cn has total volume less than epsilon. And the W's, all the elements of U, are a cover of Cn. So it has to have total volume greater than or equal to epsilon. So this is greater than or equal to well, I guess technically this would be strictly greater than, because F has a point in W which evaluates to a number which is strictly greater than 1 over n. But that doesn't really matter. All that's really important is that we're getting a lower bound. It doesn't matter if it's greater than or equal to. But anyways, so the sum of the VWs must be greater than or equal to epsilon. And we keep the n there, so this is all greater than or equal to epsilon over n. Okay, so what this means is that this holds for any partition of A. So the infimum over all partitions P of the upper sum of Fp must be greater than or equal to epsilon over n. Right? Because this inequality is true for any particular partition. So it will be true when we take the infimum. Now this contradicts the fact that the infimum of these upper sums, well, what is this? What we know is that this is we know that this is equal to the integral because this is an integrable function. And this integral, we're told, is 0. So the infimum of the upper sums must be both 0 and must be greater than or equal to epsilon over n. So we have a contradiction. So thus, it cannot be the case that the measure of Cn is non-equal to 0. So the measure of Cn must be 0. Okay, and this holds for any n. So let's just state that this holds for all n. Now let C be the union from n equals 1 to infinity of Cn. And now what is this set equal to? I claim that this is equal to the set of all points x such that f of x is not equal to 0. I'm going to talk through the logic behind this. You might need to write this out if you're doing this for an assignment, but I think this is straightforward enough that I can talk through it. So if you have what you do, again, we're talking about equality of sets, so we need to prove by inclusion. So you take an element in C, then it needs to be in the set on the right. You take a point in the set on the right, then it has to be in C. So if you take a point in the set on the right, so a point x, where f of x is non-zero. F is positive, so f of x is greater than 0. So it must be greater than 1 over n for some arbitrarily large n. Or there must be some n large enough such that f of x is greater than 1 over n. So x is in this particular Cn. And so that means that x is in the union of all of the Cn's. And so that means that it's in C. So that means that the set on the right is contained in C. Now for the other direction, take an element in C, then this element is in any element in C must be in some set Cn. So if you take x in C, this x is in some Cn. And Cn contains all points where f of x is greater than 1 over n. So f of this particular value of x is greater than 1 over n. And that's certainly going to be greater than 0, so f of x is not equal to 0. And so this x value is in the set on the right. And so therefore C is indeed equal to this set on the right. Okay. Now what we want to do is that this has measure 0. Now that's straightforward now because the measure of C is 0 since the measure of Cn equals 0 for all n. And so that means that C is a union, a countable union of sets of measure 0. And one of the theorems from the previous section is that a union of sets of measure 0 has measure 0. And so therefore, C, the set of points where f is non-zero, has measure 0. And that's the exercise. Again, I don't know if it's even true that the CNs all have content 0. And if we look at this, like where would that have come into play? So what we did is we took this subpartition fancy squiggly U here, containing all points W, which basically this is a subpartition. This is a collection of sets which covers Cn. And I have no idea if there's a way to guarantee that this has that this is a finite collection. And indeed, I'm sure you could come up, I feel like something tells me that you could come up with a partition where this collection U has to be infinite. And so there might not even, in that case, there's not even a way to prove that that Cn has content 0. It has to be that Cn has measure 0. So I guess this is still stumping me. And so, like from a mathematical perspective, there's something about like if you're, like you want to know everything you can know. So if it is true that this, even though we've done the exercise, if it is true that each of the CNs has content 0, we'd like to be able to figure that out. And so this does feel a little bit incomplete in that sense, but I don't know how to do that. And since it doesn't seem to be necessary for this problem, I'm fine skipping it and just keeping the solution to the problem. So yeah, I think that this is a sufficient, well, it's certainly a sufficient solution to the problem, and I'm not too worried about this CNs having content 0, and so I think we can be satisfied with this solution.